My name is Benjamin Dingle, and I'd like to thank the organizer for inviting me. The title of my presentation is Linearized Microwave Photonic Devices for Microwave Fiber Links-Based 5G Application. The objectives of these presentations are the following. One, to introduce three linearized microwave photonic devices, which is shown in this figure. And then to discuss some of the unique features of these devices. However, because of the limited time, I'll be focusing only on one device, which is the frequency discriminator for 5G application, shown by figure number 1. Now, with the COVID-19 pandemic as the theme of the conference, it is important to realize the enormous role of the information and communication technologies to maintain our human interaction, even though it might be long distance interactions. Now, the information and communication technologies here are divided into three networks. One is the digital optical fiber systems, which consists of the internet as well as the data centers. Number two, the analog optical fiber communication, which involve the CATV, broadband access, remote antenna, as well as the satellite communication link. The number three areas or aspects is the wireless network, of course, involving the wireless 5G network as well as the remote access network. Our interest in this paper is the interface between the the analog optical fiber communication and the wireless. And this is usually represented by this symbol here, which we indicate to be in the figure number 2. This interface is generally known as the microwave photonics link. So what is a microwave photonics link? Technically speaking, microwave photonics link consists of three parts. One is the transmitted module and the optical fiber and the receiver module. The transmitter module and the receiver module are connected by the optical fiber that could have a length from 1 kilometers to a few tens of kilometers. Because the microwave photonics link is a analog system, it is important to linearize the whole link, and this involves linearization of the transmitted module as well as the receiver module. So in the research trend in the microphotonics, first we will discuss the commercial side. In the commercial side's implementation of the microphotonics link, the general standard use is to employ the intensity modulated direct detection scheme, which is illustrated or indicated by figure number 4. In the transmitted module, it has the laser and the intensity modulator. And then the RF signals injected into the modulator and transmitted into the fiber. The receiver section consists of only a photodetector. So the advantages of the intensity modulated direct detections are the following. One, it's low cost. Second, it has a very simple receiver design module. However, the disadvantage are the following. It requires a good linearity in the transmitted module, meaning to say that it requires a linearized modulator. Together with the linearized modulator, you have to be concerned about the biasing problem of any modulator. So that's another difficulties. Also, the power threshold problem must be resolved or must be maintained. Intensity modulator tend to have a very high peak-to-peak power output. The most dominant device that can introduce nonlinearity is the modulator. So we need to linearize the modulator. In the research stage, there's a growing demand now to investigate an alternative to the intensity modulated direct detection. And this is to use the frequency or phase modulated direct detection scheme as illustrated by figure number 5. The advantages of this schemes are the following. One, it has a higher capacity with advanced modulator format, simple transmitter module with no biasing problem, higher threshold power as well as higher link gain. However, the disadvantages now is in the linearization of the receiver, which require more sophisticated design. And one of the important key element in the receiver module is what we call the PM/FM to IM converter. Now, the need for this is we need to have a very simple converter design, but a very high linearized one. Now, this table illustrates the different technologies available or have been reported with regards to this one. For our purpose, we will only be concentrating on one of the design aspect of it, which is the frequency discriminator, and in particular, the electric field discriminator. We will be focusing on our design, in which we call Sign 2. Now, as I mentioned previously, there are many different types of converter, and we will be working on frequency discriminator. There are two types of frequency discriminator. One is the linearized intensity modulator, and linearized intensity frequency discriminator, and the other one is the linearized electric field frequency discriminator. The requirement for this discriminator are the following. Number one, it has to have either be linear in amplitude or intensity, but also must have a linear phase as much as possible. It is also desirable if they can have a programmable features, which we will be discussing later on. Now, an important aspect in the overall design that is related to the 5G are the following requirements. One, the linearized modulator must have a low complexity design, which means fewer components within the design. It must also have a small footprint and lower insertion loss, low cost, and low power consumption. The question that you might ask is why all those requirements? So those requirements are necessary because in the standard implementation, usually the transmitter module is located in the base station, a bigger base station, and then whose signal is transmitted through the optical fiber down to the donor unit, or probably we call power box. The power box has the receiver module, and then that receiver module, the signal from the receiver module is transmitted by a coaxial cable into the antenna system. Now, in the 5G application, 5G network implementation, the donor box or the power box is removed. Now, the transmitted signal from the transmitter module is now directly attached into the antenna. So we put the receiver module as much as possible near to the antenna. So that means it requires that the receiver module must have a low power consumption, must have a low size or low footprint, and also low insertion loss, so that it could be put near to the antenna itself. Now, what is the state of the art in terms of the linear electric field frequency discriminator? Here, table 2 shows all the different technologies that have been reported in literature in terms of the electric field linearity in the y-axis, and in the x-axis is the number of stages or element that is used in order to obtain high linearity. High number of stages also imply high complexity. Here we can see that as the number of stages or element is increased, then you can get a higher linearity as shown by this table here, figure. But it also implied the following. High linearity appears to have involved too many Mach-Zehnder and ring resonator, which lead to the following problem. Why? It would require higher power consumption. it will also require a larger size of the footprint of the chip, and also higher insertion loss. So there is a need to develop a linear frequency discriminator that have low complexity. And recently we proposed such design, and we call this linear frequency discriminator sine 2 frequency discriminator. It consists of two Mach-Zehnder design and one branch combiner, as shown in this figure number 8. The linearity characteristic is also shown by figure number 9. It is the red line over here. The green line represents the typical Mach-Zehnder output profile. There are two ways of assessing the linearities of the sine 2 that involves slope analysis using Taylor expansion, or the two-tone measured by the Sperry dynamic range. We will not discuss the mathematics behind it, but the process is typical. Now, here are the unique features of sine 2 frequency discriminator in comparison with Mach-Zehnder interferometer. In the Mach-Zehnder interferometer, you can see that the slope is here is -1. The Mach-Zehnder profile is given by the red line. However, the bandwidth utilization range is very, very low over here. Compared with sine 2, it has almost double the bandwidth utilization portion, although the slope of the sine 2 is now lower, given by -0.6. It also shows the good features of the deviation, as well as the linear phase of sine 2 over here. Now, the other features of sine 2 in summary form are the followings. Number one, it has a selectable dual slope, switchable slope, and tunable bandwidth. Um, um, uh, as long as we can maintain, these features are obtainable if we allow the path length difference of the Mach-Zehnder to be tunable. In terms of the position of the sine 2 in the state of the art, here we can see that the sine 2 has a low complexity because it uses only two Mach-Zehnder design, but it has a high linearity. So it is very desirable and very useful. Now, in conclusion, we have presented an electric field frequency discriminator for 5G application, especially for receiver module. We have reported some of its unique properties, including low complexity, low power consumption, low insertion loss. I like to report that the publication and the characterization of this device is scheduled to be presented next month in the Microwave Photonics conference. So I did not include it in my presentation. We will also be presenting a more optimized or a more minimalist design of the sine 2 next year in the SPIE Photonic West Broadband Access Communication Conference. I would like to acknowledge my um, uh, collaborator and student that made this possible. Thank you very much.